everyone, welcome to my channel Chemistry by ANR. Today we are going to study about carboxylic acids. Do you know what acid is present in the sting of ants? Do you know what acid is present in rancid butter? Do you know what acid is present in vinegar? Formic acid is the acid that is there in ant bite. It pains a lot, right? And it swells. And what? Butyric acid is present in rancid butter. Rancid butter means the butter that has got spoiled. And another thing is what? Vinegar. Vinegar में कौन सा acid है? Acetic acid. So we come across so many acids in our daily life unknowingly. And do you know what acid is secreted in our stomach? And we say we have acidity. What acid is secreted? They are not organic acid. Okay, so acids may be organic acids and mineral acids as well. The acid that is secreted in our stomach causing ulcers and all is HCl. But the acids that we will be discussing about are organic acids that are present in plants and animals. So let us explore new concepts today. Hello everyone. Today's discussion is on methods of preparation of carboxylic acid. The nomenclature part of carboxylic acid is covered up with the carbonyl parts, aldehydes and ketones. So starting with the preparation of carboxylic acid, let us see from primary alcohols and aldehydes. Carboxylic acid can be prepared from primary alcohols by the method of oxidation. So since we know that primary alcohols are 1 degree alcohols, so RCH2OH on mild oxidation gives you RCHO, which again on oxidation gives you RCOOH. So if I can use a suitable oxidizing agent, a strong oxidizing agent like alkaline KMnO4, or say acidified K2Cr2O7, then in that case, so for this followed by hydrolysis H3O+. So I can use alkaline KMnO4 or I can use K2Cr2O7. I can use CrO3 in acidic medium. So if I use K2Cr2O7, I will write acidified K2Cr2O7. Okay, so acidified K2Cr2O7. This is what I need to write. That is a strong oxidation step from 1 degree alcohol to carboxylic acid. Or I can use Jones reagent. Jones reagent means same thing, acidified CrO3. That is known as Jones reagent. So when I use Jones reagent, the CH2OH gets converted to COOH. It is a strong oxidation method. Next from alkyl benzene. So when I say alkyl benzene, whatever is the structure of this alkyl group, the entire alkyl group gets converted to COOH by using KMnO4KOH heat followed by hydrolysis. So irrespective of the length of the side chain, irrespective of the structure of the side chain, suppose I say I want to obtain benzoic acid from styrene. Now styrene is CH double bonded CH2. This is styrene. So when I want to get benzoic acid, number one, I will give KMnO4KOH heat. So I will write KMnO4KOH comma heat, and number two I will write H3O+. If I do so, then I can get benzoic acid. So the double bond is not getting affected. Instead, the entire structure, entire CH double bonded CH2, this part is getting oxidized to COOH. Okay, so after this we have from nitriles and amides. So nitrile means RCN. So we can write RC triple bonded N. This is the structure of CN. So CN gets converted to COOH. Here CN is getting converted to COOH, and it is a hydrolysis method where it is hydrolyzed to first amide. Amide means C double bonded O NH2 linkage. This is known as amide linkage, and then it is actually converted to acid in acidic or alkaline medium as the catalyst. So here what is happening is RC triple bonded N, this side, it is hydration almost occurring with oxygen getting added to the carbon end and H2 getting added to the nitrogen end. So I can write RC double bonded O NH2. I have already written it over here. So this is it, RC double bonded O NH2. So nitriles are hydrolyzed in presence of H plus or OH minus to give RCO NH2, which is amide. Now, amide on heating with H plus and OH minus will give you acid. So you can imagine that yes, here the bond is breaking and carbon end is having OH, nitrogen end is having H. So then we will get RC double bonded OOH, that is carboxylic acid. So ethanamide again will get converted to ethanoic acid and ammonia. How? See, ethanamide, that means what? I can say RC double bonded ONH2, just like this case. So what has happened here? OH and here H is getting added. So we got ethanoic acid and NH3. Benzamide. Okay, it is benzenamide, so benzamide. C double bonded O NH2 with the benzene ring. So I can write AR over here. Again, I can break the bond here. I will write OH. I will write H here. So what I got over here is AR C double bonded O OH. So this is benzoic acid and NH3. Next, from Grignard reagent. So Grignard is RMGX. So it reacts with carbon dioxide or dry ice, not the gaseous carbon dioxide. Solid carbon dioxide is known as dry ice. So what happens over here is, just as we have seen in coal-based reaction, when I told you that CO2 acts as a weak electrophile. So here C end gets a delta positive character, for which the R minus or R having a delta negative character can attack the carbon end and oxygen opens up, becomes O minus. So this is carbon dioxide, C double bonded O remaining as it is, and O minus holding MgX. So it becomes OMgX. Followed by hydrolysis in acidic condition, the bond breaks and oxygen holds H and the other magnesium holds OH. So I get RC double bonded O OH plus MgOHX. This is what is happening. Okay, so as we know, Grignard reagents and nitriles can be prepared from alkyl halide, what we have seen previously. So we can prepare RCOOH from alkyl halide itself. Now this reaction is very useful for converting alkyl halide into corresponding carboxylic acid having one carbon atom extra. Having one carbon atom extra means it is having one carbon atom more. Okay, so this is known as ascending series. This is the ascending process, or it is known as the step up method. Why the step up method? Because in the product we are having one carbon atom extra. So if we start with Rx, obviously giving Mg over dry ether medium, I will get RMGX, and Rx was having n number of carbon atoms, n carbon atoms, but now this Rx is having RCOOH with n plus 1 number of carbon atoms. I hope why I told step up method, why it is an ascending method is clear. Moving on to preparation of carboxylic acid from acyl halide. Acyl halide means C double bonded OX or Cl when I say acyl chloride, and anhydride means RC double bonded O. Here again an oxygen, C double bonded O, and R, that is RCO whole twice O. You know what? Anhydrides are prepared from 2 moles of acid by the removal of 1 mole of water. Suppose I take this COOH, RCOOH 2 moles, and I remove 1 mole of water. What I will get is acid anhydride, RCO whole twice O. So these can be hydrolyzed. So RCOCl can be hydrolyzed with water. It can also undergo alkaline hydrolysis followed by acidification finally. So these are the methods by which you can obtain carboxylic acid. Remember, in this type of compound where I have 2 different structures on both the side, I will get mixture of acid. Next, from ester. We can obtain ester from carboxylic acid. So we can again get back the carboxylic acid from the ester by acidic hydrolysis. Now, not only acidic hydrolysis, while basic hydrolysis also gives you, but not directly the acid, but the carboxylate we will get. Let us see one by one. When I give acidic condition, then it hydrolyzes to form COOH. How? Because this linkage is C double bonded O, OR. So obviously, if it is breaking, this end is holding OH and this is holding H. So ROH is the alcohol. So I got C2H5OH over here. The rest part is the acid. So I got benzoic acid over here. And under basic hydrolysis condition, I will get carboxylate ion. So this is COONA because I have used NaOH. If I use KOH, I will get COOK, which is followed by acidification to obtain the acid and the alcohol. Since we can obtain ester from acid and alcohol when we are undergoing hydrolysis of the ester, be it acidic condition, be it basic condition, we finally land up to acid and the alcohol only. Now, example 8.5. Here the solution is given. What is supposed to be done is conversion. How can you convert butan 1-ol to butanoic acid? So 1 degree alcohol gets converted to butanoic acid. I have many ways to do it. I can give Jones reagent. I can give alkaline KMnO4. So what will I do? I will give KMnO4. I will add KOH to it, which makes it alkaline, heat it, and finally I can give H3O+. I can give acidified K2Cr2O7 as well. Benzyl alcohol. Benzyl alcohol means the benzylic position is having OH. This is your benzylic position and this is having OH. So this is benzyl alcohol. I have to prepare phenyl ethanoic acid. This is quite an important example. So if I prepare phenyl ethanoic acid, means I am just converting CH2OH not to COOH but increasing 1 carbon atom. So this is a step up method, ascending method. So I can use nitrile. For that, I have to convert it to RX and then I can convert it to RCN. So I have been given alcohol. So treat it with HX and you get RX. So you can straight away give SOCl2 also and you can get C6H5 CH2Cl as well, just like the previous cases in the previous unit. you can give KCN and then convert this RCl to RCN. And then follow acidic condition hydrolysis, convert CN to COOH. Whenever you want COOH, please try to find out a suitable method that converts the starting compound to CN, and then by hydrolysis you can obtain RCOOH. Next, 3-nitrobromobenzene. That means this, that to 3-nitrobenzoic acid. So nitro remains same. Br is converted to COOH. Again, I will say it is a step up method. So Grignard reagent is used because when you give Mg, see here starting material was alcohol. So if I have to give Grignard, I have to give Grignard to the Rx step. But it's not required because I want to decrease the number of steps. Here the starting material is only having halide. So when I give Mg dry ether medium, I will get MgBr. Now I can give CO2, dry ice, and what happens is this R minus is attacking and this opens up as O minus holding MgBr, followed by hydrolysis and you get the carboxylic acid. So it is ascending method, step up method. Next, 4-methyl acetophenone. So this is your acetophenone. In the para position there is methyl, so 4-methyl acetophenone. Converted to terephthalic acid. Again I will say this is a common name which you have to remember. Terephthalic acid is benzene 1,4 dicarboxylic acid. When you are studying this, please keep a copy beside. Simultaneously write down. When you write, you don't forget, you retain longer. So benzene 1,4 dicarboxylic acid. This can be done by using alkaline KMnO4, keeping in mind that whatever is present in the side chain followed by acidification, of course, gets converted to COOH. So likewise I can say, can you convert acetophenone to benzoic acid? Yes, same thing. Acetophenone is this. If I want to convert it to benzoic acid, it is this. So what will I do converting it to benzoic acid? I will use alkaline KMnO4. So KMnO4, KOH, comma heat, number 2, H3O plus. Okay, so then I will get benzoic acid, and then in this case also I am getting benzene 1,4 dicarboxylic acid. Next, cyclohexene to hexane 1,6-dioic acid, adipic acid. Now when I say adipic acid, it is a dicarboxylic acid. Remember the mnemonic which I gave, Ohm's gap? That is what a dicarboxylic acid can contain minimum 2 carbon atom, and the name is oxalic acid. So total number of carbon atom when it is 2, it is oxalic. 3, it is malonic. When it is 4, then succinate. Then 5, glutaric. 6, adipic. 7, palmitic acid. So here it is having total 6 carbon atom. So 1,6-dioic acid is adipic acid, common name. How to do this? It was a cyclic compound. It has got to an open chain. So remember that this is a special type of reaction where you use KMnO4 under acidic condition, H2SO4, and you heat it. Suppose I give you this type of compound. I give you unsaturation on both the sides, okay, and then I give you KMnO4 and acidic condition, H2SO4, followed by heat. What will be the product? Same ways, you break it over here and add the last carbon becoming COOH. This is a COOH, this is a COOH. Likewise, this carbon becomes COOH and this carbon also becomes COOH. See this structure and this structure is the same. So my product will be 2 moles of COOH, CH2, COOH. Dicarboxylic acid containing 3 carbon atoms. So where 3 carbon atom malonic acid we have got. So this is how you can make these compounds react with KMnO4 in presence of acidic medium and heat. Next, butanal aldehyde getting converted to butanoic acid. Oxidation, use a mild oxidizing agent. We know toluene and phenolphthaleins are mild oxidizing agent. So ammoniacal silver nitrate, mild oxidizing agent. It will convert it to butanoic acid. See, the number of carbon atom remains the same. 1, 2, 3 and 4 on the reactant and the product side, both. Next, Intext question 8.7. Show how each of the following compounds can be converted to benzoic acid. Ethyl benzene, we have seen it. See, ethyl benzene means there is a CH2, CH3 here. So when I do so, what will I do? It's a CH2, CH3 here. So when I do so, what will I do? I will actually give number 1, KMnO4, KOH, heat it, number 2, H3O plus, and I'll convert it to benzoic acid. Acetophenone to benzoic acid, just now I have shown you. Bromobenzene to benzoic acid. Can you guess what to do? Here we have started only with a compound which is having halogen. So let's see, likewise here. Convert it to Grignard, give CO2 and then followed by H3O plus. So what we will do? First convert it to Grignard. So Mg in presence of dry ether. Then you will get this thing. Convert it to phenyl magnesium bromide. And then what will you do? Give CO2 number 1, number 2 H3O plus, and then you will get completely this getting converted to COOH. Next, from styrene I have already showed. From styrene I have shown it to you. It is what? This is styrene, CH double bonded CH2. This getting converted to benzoic acid. Chalo, I am showing it once more. So what it is? This is COOH. Remember the combination. KMnO4, KOH, comma heat, number 2 H3O plus. So whatever is present here gets converted to COOH. That was the application of the concept. Now, moving on to physical properties, we have 2 things to discuss. One is boiling point and the other is solubility. Everywhere we have discussed in this manner only. Boiling point. So when I say boiling point, carboxylic acids have higher boiling point than aldehydes, ketones and even some alcohols. Why you know? Because it can form associated molecule on account of intermolecular hydrogen bonding forming dimer. That means one unit getting converted to another. It is not in the same structure but one molecule to another. That's why intermolecular. You may think, why ma'am it is intermolecular? It can be intra. No dear. Intra it cannot be, because if it is intra then within RCOOH only the hydrogen bonding will be. But here we can see the hydrogen bonding is existing between one unit of RCOOH to the other unit of RCOOH. Okay, so the hydrogen bonds are not broken completely even in the vapor phase. So it's very strong and thus it has a high boiling point. Next, solubility. Lower carboxylic acids will be soluble on account of the formation of intermolecular hydrogen bonding. However, if the number of the carbon atom goes on increasing, then the solubility decreases. Why? Because hydrophobic interaction goes on increasing if I am talking about higher carboxylic acid. Next, After the preparation and the properties, we move on to chemical reactions of carboxylic acid. Since it is an acid, the main role will be the acidic behavior. To show the acidic behavior, you can show the liberation of H2 with active metal like sodium, the formation of salt and water with base which is NaOH, the liberation of CO2, carbon dioxide with bicarbonates. So these are the evidences that shows the acidic behavior of carboxylic acid. Carboxylic acid dissociate in water to give what? The conjugate base which is known as carboxylate ion. This carboxylate ion is resonance stabilized, and please see it forms two equivalent resonating forms. As it forms two equivalent resonating forms, the contribution of each resonating form to the original structure is same, and we can say 1:1. Also note that the negative charge oscillates between two electronegative oxygen atoms only. So the two resonating forms are equivalent, so extra stability is attained and the negative charge resides in the more electronegative oxygen atom. For these reasons, the carboxylic acid is even more acidic than phenols. This is the acidic behavior of carboxylic acid. But when I talk about carboxylic acid, let us see one more thing, then I am coming to it, that when I am talking about this reaction with water, so at equilibrium, K equilibrium, the equilibrium constant is the product of the molar concentration of the products by product of the molar concentration of reactant, and after some time we will see that the molar concentration of H2O remains almost the constant. You multiply that with the equilibrium constant and get the acid dissociation constant Ka. Now, how is pKa related to Ka? pKa is equal to negative logarithm of Ka. So, it has inverse relation with Ka. When the Ka value is more, strength of the acid is also more. And since Ka and pKa has inverse relation, so I will say a lower pKa value means a greater acid strength. So after this, all these things are discussed. Whatever I have said is discussed in these paragraphs. Next, I move on to the effect of substituents on acidity of carboxylic acid. Now, greater is the stability of the conjugate base, greater is the strength of the acid. Now, if there is any electron withdrawing group, then it causes better negative charge delocalization. Remember one thing, any factor that reduces the charge over the atom is delocalization, and any factor that increases the charge density over the atoms is destabilization. So if it is an electron withdrawing group, then it takes away electron density towards itself, means reduces the negative charge density that exists between the two oxygen atoms on account of the resonance. So this causes better negative charge delocalization and hence greater stability of the conjugate base and hence greater acidity of the corresponding acid. For an electron donating group, it increases the negative charge density over this system, for which the negative charge concentrates more and is destabilized. Conjugate base is destabilized. Strength of the acid is less. Next. These are the effect of the groups that increases acidic order. Okay, acidity. Remember what I said, that if acidity is greater, means it is a better electron withdrawing group. These are better electron withdrawing groups. So this is electron withdrawing nature increases. Electron withdrawing nature increases in this order, and so the acidic strength also increases in this order. Next, what we can say is these are the acidic strength based on pKa values. If the pKa value is more, means the acidity is less. Okay, so here we can see the acidic strength, okay, increases in CF3COOH. Why? Because a more electronegative atom. So fluorine has greater electron withdrawing effect than chlorine. Now here 3 chlorine is there. So number of electron withdrawing group. This is electron withdrawing effect of fluorine greater than chlorine. So the acidic strength is greater. Now here and here what is happening? The number of electron withdrawing group is decreasing from Cl3 to Cl2. Then you go to NO2. Electron withdrawing group, but it has less than that of Cl, which is more electronegative. Move on to Cn, electron withdrawing group, but less than that of NO2. That is the order. It goes on in this manner. So I can say that electron withdrawing effect, if it is greater, then acidic strength or acidity will also be greater. And I can say if the number of electron withdrawing group increases, then acidic strength also increases because the electron withdrawing effect increases. Direct attachment of groups such as phenyl or vinyl to the carboxylic acid increases its acid strength because it is actually giving stability to the conjugate base on account of this resonating form. Next, electron donating group like OCH3. It reduces the acidic strength over COOH because it increases the electron density over COOH. So this is less acidic, having a greater pKa value than that of benzoic acid, which is again less acidic than nitrobenzoic acid, which is electron withdrawing group having a lesser pKa value. So this is the reason which we have talked about. Next, moving on to reactions involving cleavage of COH bond. The carbon oxygen bond breaks. In RC double bonded OOH, this bond is breaking. When we were talking about acidic behavior, oxygen to hydrogen bond was breaking. Now formation of anhydride. This I have already told you that when 2 moles of acid undergoes dehydration, of course in presence of dehydrating agent like concentrated H2SO4, P2O5 under acidic condition, they undergo dehydration. So it is removal of water, which I have highlighted, and you get the corresponding anhydride. Next, which I have already said, that an acid reacts with an alcohol in an acidic medium, that is concentrated H2SO4, gives you sweet fruity smell of ester. This is used as a test for carboxylic acid and also alcoholic OH group in your practicals. Alcoholic OH group also gives test like steric ammonium nitrate test, where you use the sample and you treat steric ammonium nitrate to it, then you will get a red coloration. So this is a test for alcoholic OH group apart from esterification test. In esterification test, you take the sample, say carboxylic acid, treat it with ethanol, add few drops of 2 to 3 drops of concentrated sulfuric acid and heat it in a water bath. You get a sweet fruity smell of ester, fruit-like smell. Now, next is ring substitution. That means aromatic electrophilic substitution. Carboxylic acid, COOH group, the carboxylate group, the carboxyl group rather, is electron withdrawing group. It is electron withdrawing group. Why? How does it withdraw electron? See, when I am drawing the structure of benzoic acid, I can say that the electron density moves out of the ring, outwards, decreases the electron density over the benzene ring on account of -R effect. for which it is deactivating, for which it is meta-orienting. So if there is an electrophile, it will always occupy the meta positions. Okay, so nitration is an example of aromatic electrophilic substitution where NO2 plus is acting as the electrophile. So it attacks the meta position because due to resonance, due to minus R effect, the electron density is relatively greater over the meta position. Because here what happens is, in the resonating structure you can see that there is a double bond here, CO minus and OH here, generating a positive charge at the ortho position. So obviously in the next resonating form, the positive charge will come to the next para, and in the next it will come to the ortho. So I can say the electron density over the meta position is comparatively greater in comparison to ortho and the para position. So here there is a positive charge in the ortho position and the para position. So nitro group is entering the meta position. This is the meta position. Okay. So next there is one more important point, that benzoic acid or aromatic carboxylic acid does not undergo Friedel-Crafts reaction. Why? We have seen it is deactivating in nature. So it does not undergo Friedel-Crafts. Moreover, the Lewis acid, aluminium chloride, anhydrous AlCl3, what happens is it is electron deficient. So it takes the electron from this rich center and it gets bonded to the carboxyl group. So for these two reasons, it does not undergo aromatic carboxylic acid, does not undergo Friedel-Crafts reaction. This is a reaction which is bromination. Again in the meta position, the bromine has come. So it will not undergo Friedel-Crafts alkylation or acylation, but it undergoes nitration and bromination like reaction. The Intext question, which is more acidic? CH3COOH and the other one is CH2FCOOH. Fluorine is there, which is an electron withdrawing group, and hence the acidic nature is greater here because it releases H plus easily and it stabilizes the conjugate base, the carboxylate ion. Next, here there are two types of electron withdrawing group, one fluorine and the other chlorine. So the electron withdrawing effect of fluorine is greater than that of chlorine. So this will be more acidic. Next, I am having what? I am having fluorine over here, and I am having, just a minute, and I am having, see, I'm having a fluorine over here and a fluorine over here. What is the difference? Both are to fluorine. Difference is this is carbon number 1, this is carbon number 2, and carbon number 3 having fluorine. Carbon number 1 and carbon number 2. Okay, 3. This is 4. Carbon number 4 having fluorine over here. Okay. So this is having fluorine because this is CH2F. And here carbon number 3, CHF, 3 is having fluorine. Okay. So the electron withdrawing group, fluorine, is closer to COOH, and so it is showing greater electron withdrawing effect and hence stabilizing the conjugate base more. So this is more acidic because it is closer to the COOH, and here it is in carbon number 4. Next example, it is having CF3 and here CH3. Greater number of electron withdrawing group here, 3 fluorine. So obviously the electron withdrawing effect is greater and it stabilizes the conjugate base, which is the carboxylate ion. So that's all for today's session. It completes the carboxylic acid part and hence the chapter aldehydes, ketones and carboxylic acid. I hope you enjoyed the interaction. Try to interact in the comment section with me, where I will definitely reply to your comments. So let us explore some more new concepts in our next upcoming sessions. Till then, bye all of you.